Hello everybody and welcome to our first exercise looking at a single factor analysis of variance. So single factor because when we get through these problems, the last set that we'll do is called a factorial, and that one's actually two factors or two variables that we'll be working with. So we'll start off simple. It's not going to feel simple at first, but we'll get through these. Single factor analysis of variance. So this is what is called a completely randomized experimental design. That completely randomized experimental design, of course, this is one where the experimenter has some control over the application of treatments to the experimental units, as opposed to an observational study, which is really methodologically, the calculations are identical, but the way the data is collected is a little bit different. For an observational study, it's as if the data is already out there and I'm going out and I'm collecting data and then I'm comparing that data. In this one here, I am effectively creating a data set. So I can control how my treatments are being applied to those experimental units. So let's just jump into this exercise, and I'll talk about a few of the little challenges that can come up as we go through. White Tooth Inc. is developing an additive for its line of toothpaste that is designed to whiten teeth in as little time as possible. It currently has two variations of the additive, type A and B, but only wishes to produce and market one of them. In order to determine the effectiveness of these new additives, we take a focus group of 28 people. 9 of them are given type A, 9 of them are given type B, and 9 of them are given a placebo. Well, clearly we don't have 28 people. That must be a typo. We have 27 people. Each person is asked to use the toothpaste and record the time in days it takes before their teeth achieve some predetermined shade of white. Okay, so we're whitening our teeth. Our data here is measured in days. This is also known as our response variable. And we're wondering if that response variable, the time, the number of days that it takes before I see my teeth turning white, is it influenced, is it somehow related to the type of whitener that I'm using? Either type A, type B, or maybe it's no different than a control group, which is using just regular toothpaste. So, of course, they don't know it. It's a placebo, right? So, here's that data set. Now, what you would normally have to do is calculate all of those sample means and those sample variances. So here, these are our X bars, and these are our sample variances S squared. So what we're going to do in this exercise, we start off stating our null and alternative hypotheses, same as always. Then we've got a few steps to go through in producing what is called an ANOVA table. And so the ANOVA table is going to look something like this, where here we're going to have, first of all, our source of variation. Because this ANOVA, analysis of variance, is all about accounting for different sources of variation. Now, in the introductory video to Module 13, I talked about the sum of squares due to treatment, right? That was SSTR. I also talked about sum of squares due to error. That was SSE. And if we add together those two sources of variation, SST and SSE, well, that gives us sum of squares total. So we will be working with, throughout this module, this relationship where the sum of squares total, the total variation in our data set, can be partitioned into its various sources. And here we are starting with The simplest one, again, it's not going to feel simple at first, but of the ANOVA test, this one is the simplest, and we're going to be dividing it into two sources of variation. In the later exercises, we'll be accounting for some other sources of variation in that data set. So our ANOVA, we're going to calculate SST, SSTR, SSE, and SST. We'll have our degrees of freedom. When we divide those sums of squares by degrees of freedom, we get the mean square. Then we'll have our F. Then we'll have our P. And then we can also include in here our critical value. So this is the table we're going to fill out to come to our final conclusion. Let's get into this. Our null and alternative hypotheses is that the mean of type A is equal to the mean of type B is equal to the mean of the control. In other words, there's no difference between them. The alternative, not all are equal. Again, it's a really common mistake. I see students make this mistake all the time to write this like this. Not equal, not equal. Because that would be consistent with how you've seen other tests for equality, right? It's either equal or it's not equal. But that's not what we're testing for. That might be the case. But this initial test is only to determine that not all of them are equal, or at least one is different. And then for those of you, if you went through Module 12 and you saw a similar test on multi-population proportions, well, we went through, if we rejected the null hypotheses, then there was this other test that we did to determine where the difference exists. Well, same here. Here it's called Fisher's LSD, the least significant difference. So if we have evidence to reject the null, at least one of them is different, then we go through this next set of tests to identify where the difference exists. Okay, so we have our test. Now we need to determine what is our best estimate of the unknown population mean that would exist if the null hypotheses were true. So we need that grand mean. Now, the grand mean is generally your safest approach to calculating the grand mean would be as a weighted average of the sample means. This should always be kind of the first thing that you go to. If and only if, so if spelled with two F's there means a very strong if and only if your sample sizes are equal, which for us they appear to be equal, well then I can factor out that n, and this becomes x bar 1, x bar 2, x bar 3 divided by 3n. And so my grand mean becomes just the mean of the sample means. So here I can see my sample means are identical. Sorry, not my sample means, my sample sizes are identical. So I'm going to use that formula and I'm going to calculate the mean of the means to obtain my grand mean. So here they are, 6 plus 5.56 plus 7.33 divided by 3. So my grand mean is 6 plus 556 plus 7 1/3 divided by 3. And my grand mean is 6.297. Okay, now we have a few calculations to go through. The first thing that I'm going to do, we always would start here in this first square. This is sum of squares due to treatment. So SSTR This is looking at the difference in sample means and the grand mean squared, and we weight that by our sample size and add those up across our 3 treatments. I keep running out of room. There we go. Okay, so here I have my sample size. Each of those samples contained 9 observations. So now I'm going to calculate these 3 differences. Each one we multiply by 9, and these are all squared. So I have my sample means 6, 556, and 733. So here's 6, 556, and 733. And our sample mean, grand mean I should say, 6.297. So here's 6.297. I gave myself decreasing level amount of space here, 297. There we go, we can squeeze that in. Now we'll go through and calculate these. Now, you can see here when we have identical sample sizes, there's often shortcuts. One of those shortcuts we saw was calculating the grand mean as just the mean of the means. And now also I can see that I could factor out that 9 and just reduce the number of calculations required here, number of button presses. So if I factor out that 9 and just calculate the whole thing and then multiply the end result by 9. So I only need to do that multiplication once. Save some button presses. So the first one, 6 minus 6.297, square that. Here I have 0.088 plus the next one, 556 minus 6.297. Here out and square that. Here I have 0.543. And finally 733 minus 6297 squared. This is 1.067. Now if I add those up, plus 0.543 plus 0.088, and now I'm going to multiply the end result there by 9, I have 15.28. Now there's often a little bit of rounding error here, so if you get something a little bit different, not the end of the world. It always depends on how many decimal places you use. So here I have my SSTR is 15.28. Degrees of freedom for SSTR is k minus 1, where k is the number of treatments. So here I have 1, 2, 3, so I have k equals 3 treatments, so 3 minus 1 is 2. That mean squared, that is always the first column divided by the second column. So 15.28 divided by 2, that gives me a mean squared treatment of 7.64. Good, that's the first row done. Now, SSE. Often a little bit simpler. SSE, so now we're adding up n minus 1 times those sample variances. Now here we have to be really careful that we pay attention to what information we've been given. Because when I come back and I look at my sample data, I already have been given the variance, s squared. It's a really common mistake that students see this squared and they want to square whatever number they put in there. If you're given the variance, it's already squared. Don't square it again. If you're given a standard deviation, well then yes, you've got to square that again. So here we have 9 minus 1, and our sample variance here I have 1.5, 178, and 175. 1.5, 178, and 1.5. Let me just confirm that I didn't make any mistakes. 178 and 1.75. Okay, now again, we're given the variance. So you do not want to square it, right? If you have the standard deviation, you square it. I know I'm repeating myself, but I hate seeing that mistake. It's so frustrating because it's a silly mistake and it's easy to make. It happens all the time. Again, I've got same sample sizes here, so I can actually use a bit of a shortcut because I can factor out that 9 minus 1 and just multiply to the product of 1.5 plus 178 plus 175. So I have 1.5 plus 178 plus 175. Multiply that by 8, and I have an MSE of 40.24. Okay, 40.24, back up here into my table. Degrees of freedom for error is NT minus K. NT is the number of observations. So here I have in that whole data set, I have 27 observations. 3 times 9, I have 27 observations minus 3 treatments. So 27 minus 3, I have 24 degrees of freedom. So 40.24, again for that MSE, first column divided by second. So 40.24 divided by 24, and I have 1.677. Okay, now I can get my F statistic. Oh, why don't we go back and we'll finish up, in fact, for total. Down here, we don't actually need these values, but a complete ANOVA table does completely partition all sources of variation. So SST, well, that's just 1528 plus 40.24. So I'm just adding up those 2 rows above, gives me 5552. Degrees of freedom on SST, and this is kind of a handy little trick sometimes. This is always NT minus 1. So NT minus 1, again, we know NT here is 27, so 27 minus 1 is 26. So this is always a very straightforward calculation, NT minus 1. You can use that to determine or to double check whether or not your previous degrees of freedom are correct, because notice 26 is also equal to 24 plus 2. The degrees of freedom will always equal the sum of all the degrees of freedom above it. So you can sometimes use that if you want to double check that you've got your degrees of freedom correct, because if you have your degrees of freedom are wrong, then your mean squared calculations are wrong, your F is wrong, your P is wrong, and that mistake follows throughout. So now I'm going to get my F statistic, 7.64 divided by 1.677 divided by 1.677. That gives me an F statistic of 4.556. Now what do we do with that? Well, now we need to go to our F tables. But before we go to our F tables, we need to know, of course, what variant of the F distribution is relevant for our problem. What determines that variation? Well, that's degrees of freedom. So here we have this F statistic with 2 numerator degrees of freedom, MSTRs in the numerator, so 2 numerator degrees of freedom, and 24 denominator degrees of freedom. So while we're at our F tables, we can get our critical value if we do this test, let's say at the 5% level of significance. And this is a distribution with 2 numerator and 24 denominator degrees of freedom. So let's go down to our F tables. And I'm looking for 2 in the numerator and 24 in the denominator. And so here we are down here. Now our test statistic was 4.5. So we're somewhere in between these two values here, which places our p-value between 0.01 and 0.025. It also allows us to find our critical value at 0.05 is 3.4. So let's go back up to our ANOVA. I have my critical value is 3.4, and I have my p-value is less than 0.025. Oh, there's too many points in there. Is less than 0.025, greater than 0.01. So, what does that mean? If our test is being done at the 0.05 level of significance, here we are. We have an F distribution. We have a critical value here, approximately 3.5. That defines the rejection space and the do not reject space. Our test statistic is somewhere up here at 4.5. Here we can see if this area that corresponds to that critical value is 0.05. I can see clearly the upper tail probability that corresponds to my test statistic is certainly less than 0.05, and in fact, looking at the tables, I can see it's even less than 0.025. So, as always, we get the same conclusion with both of these approaches. That conclusion, of course, is that we have sufficiently strong evidence to reject the null hypotheses. We have evidence to show here that among these 3 different samples, the type A tooth whitener, type B, and the control, we have reason to believe, evidence to believe, that at least one of those 3 is showing a different amount of time before the teeth begin to whiten. So, what does that mean? Perform a Fisher's LSD if necessary. Well, here it is necessary. Because we rejected, because we have found that at least one is different, now we want to find out which one is different. If we didn't reject, and our evidence supported the null that they're all the same, then it would not be necessary to look for a difference because we've already shown that they're the same. So here we rejected, our evidence supports the alternative. Now we need to do a Fisher's LSD. I will do that in a separate video. This one's gone on long enough. So thank you all for watching. I hope that this was helpful, and we'll be back real soon to perform the Fisher's LSD. Okay, bye-bye.